Yeah, all of you guys here, don't feel shy. Please switch on your cameras and your mics whenever you want to ask a question. And you can feel free to keep your cameras on even throughout the session. Yeah.
Yeah, I know as an educator, I sometimes find it tough to do online classes because I can't see people's faces. And even when I'm in a classroom, I know there are kids online, but it's, it just feels like you do want to connect with everyone. So I completely understand what so it would be really nice if students can actually turn on the cameras, and that's fine if they're still in their PJs and
yeah, absolutely.
But at least turn on your microphone and speak up if you don't want to post. And I will monitor chat for you. So I might, if there are questions coming on chat, I'll pick up from there. I guess I see people are joining the Slack channel also. Yeah, let's just give 5 more minutes. I think we can start like 9:40 our time. And sure. What time is it at your end?
It's 8 p.m. now.
Okay. Okay, I think we can get started. I just sent out an email to all the workshop students one more time and their parents. So hopefully we're still going to see people rolling in, but I think we can get started.
All right, then. Great. So hi, everyone. Very good morning to all of you. I'm Nithyasri from the Growth and Community team of Classiq. Let me quickly share my slides. All right. Right, so I hope you can see my slides. So again, very, very good morning to all of you. And so I'm representing the Growth and Community team at Classiq today, or to all of you. And I'm also the founder of She Quantum and a quantum researcher with experience across startups, governments, as well as industry and academia. So I'm very happy to be here today, talking to all of you young minds, high schoolers. And I feel that all of you are very lucky to be here today because there's a one-of-a-kind program. And thank you, Rashmi, and thank you, Dr. Gibson, as well as Prof. J.K. Swan for organizing such a fantastic initiative. And well, I hope all of you are caffeinated because we're going to jump into the world of, quantum where things are dual in nature. We'll have Schrodinger's cat dead and alive at the same time and a coin toss giving you both heads and tails at the same time. So hope all of you are ready for that. And especially I would like to say, welcome all of you future quantum computing scientists to this workshop. All right, so let's get started. Firstly, I would like to throw a question to all of you. What companies do you know that are playing a role in the quantum computing space? You can feel free to open up your mics or you can put in the chat as well the answers. Hello guys, come on. What companies do you know that are working in the quantum computing space?
I feel like we've been talking about this since the beginning of the course, but now I think people are here.
All right, guys, come on. Don't feel shy at all. And an answer is never wrong. So go ahead. What are any companies? I'm sure there are people from the industry who have given talks to you before. So what are some companies you know? You can even feel free to put it on the chat if you're shy to open up your mics.
Yeah. So I have Linda Reese from saying has quoted IBM. Kabir says IBM and Google. And then Pramiti says IBM and Intel.
Awesome. Thank you guys for your answers. You forgot the company that I'm from. I'm from Classiq. We're basically, but I would like to appreciate all of you for your correct answers. Classiq is the company that's working on revolutionizing quantum software. So when you want to apply the concepts that you've learned from across these few weeks, you want to write down software, right? You want to write down algorithms. And that is exactly what Classiq helps you with. So let's jump right in. Okay, so today what we'll be doing is, I'm sure you've been learning a lot over the weeks on quantum computing. I'll be revisiting some of these concepts to reinforce your knowledge and make sure we're on the same page. And then we'll go on to talk about what you can do with Classiq, how you can develop some small quantum programs all the way up to quantum algorithms. And finally, there will be the exciting part, which is the hands-on session where you and me will be coding on Classiq together. Okay, so before we get started, I would like to say that you are in the right place today. You are in the very right place. Quantum computing is a field of opportunities and opportunities. If you see there's something that's very different about quantum computing, if you see any other emerging technology like AI or IoT, cybersecurity, most of the funding comes from private players. So some of the names that you quoted, right? IBM, let it be Microsoft, Intel, Google, these are the guys who heavily invest into this particular technologies. But when you talk about quantum computing, there's something very, very interesting. Governments across the world, especially that in the US, is focusing a lot of investment into this field. This shows the kind of seriousness that governments across the world are showing towards this technology. Secondly, this also means that you have a lot of opportunities going forward. Next, I'm sure all of you guys are already applying for universities, and you would be majoring in computer science, you might be majoring in physics, mathematics, chemistry. One very good news that I want to give you today is that you can come into quantum computing, whichever major you take, in engineering, in STEM. That is the beauty of this field, the interdisciplinary nature of this field, where the intrinsic nature is that this field comes together at the intersection of quantum physics and computer science. And when you talk about applications, you have applications in biomedical applications, pharma, you have finance, you have in logistics, you have in supply chain. I'm sure you guys had a talk by AWS from, I think, Parminder Singh, where he would have talked about logistics, the importance of quantum computing in logistics, because Amazon is typically a logistic company, right? So these are the real world applications that you can build from quantum computing in an interdisciplinary manner. So all of you here are needed to make this field possible because it's a very young infant field, right? So have you all seen a quantum computer before? Yes or no? Let's have a quick yes or no.
I have a yes from Linda. Kabir says yes.
Awesome. I'm very happy to hear that.
Yes.
Yeah.
Awesome, I guess awesome. So they have actually obviously seen quantum computers in photographs, the ones that look like the chandelier. And of course, we've had a week long of quantum hardware introduction where we've talked about the different types of quantum computers, all the way from superconducting quantum computers to neutral atom to ion to ones that are basically ion Q. We have looked at quantum annealing. So those are the kind of quantum hardware we've actually studied. Now, of course, they have connected to the IBM platform when they were working on Qiskit, and they actually ran a program on a real quantum computer on IBM, and also used the IBM simulator. And so I guess this is probably with Classiq, this is the first time that they're getting on a platform where they're going to have access to neutral atoms like QEra or the others like IonQ. I'm not sure who all are on the Classiq platform. But in our conversations with Amazon, we were told that several different types of quantum computers from Rigetti and the others are available. So I guess we'd look at the information you provide us. But in a way, I mean, a first-hand look at quantum computers, I don't think anybody in the class has had that, but they've all been able to connect to quantum computers on the cloud. And they are aware of the different types of quantum computers and hardware that's available today.
Fantastic, fantastic. So let me just show you a quick video of a lab tour to excite all of you guys, just to give you a picture of how a quantum computer looks. This is going to be a superconductor quantum computer that is of IBM. So if you've already run a program on an IBM quantum computer, this is something that you ran it on.
So this is it. This is a quantum computer. This is a quantum computer.
Here I am seeing a real-life quantum computer for the very first time with my friend and king of tech YouTube, Marques Brownlee. And I'm finally understanding why quantum computers are such a big deal.
All right, so I think it would have been exciting to see how a real quantum computer looks and the thing that you ran your program on. So let's now move on to talk about what quantum computing is, right? So the basic idea behind quantum computing is that we want to compute using the laws of nature. And when you talk about nature, what kind of nature are we talking about? What is the characteristic of the nature around us? This is very beautifully answered by Richard Feynman in his paper, Simulating Physics with Computers. And I highly, highly recommend that you read this paper because this was the triggering point. This is the reason that quantum computers exist today. So what he says in this paper is that the nature around us is quantum mechanical in characteristic. And that is exactly why we want to use the quantum mechanical laws, for example, like superposition or entanglement, and the idea of qubits, quantum bits, to do computation. So let's have a fun quiz. What do you think this cute little doggo is doing here in this picture?
Snoozing.
All right, that's half right. To be more technical, it's 1/3 right. Any other answers? What do you think this dog is doing? He's doing something very differently. Notice carefully. All right, then. Well, I'll let you know. He's doing three things. He's sitting down, he's lying down, as well as standing. He's doing three things at the same time. So what is this? This is a classic example of superposition. So we have three states here: sitting, standing, and lying down. And we want to write down the dog as a psi state. So let's say this dog is going to be represented as the psi state. And we can say that he's in the sitting position with a certain alpha, standing position with a certain beta, and in the lying down position with a certain gamma. So this particular rule applies here, where that we want the sum of the squares of these constants to be 1. This is called normalization. And now we can find that this guy, this cute little guy here, is having a probability of being in the sitting, standing, and lying down states with a probability of 1/3, respectively. Right. So this is I think this is a very classic idea of superposition that we use in quantum computing. So secondly, let's talk about quantum entanglement with this short experiment, a coin toss experiment. So let's imagine that I have a coin. I have 2 coins, and Rashmi and I meet in Israel. I give her 1 coin. I did some magic on this coin, so it's not an independent system. Okay, so I did some magic on this coin. I gave 1 to her. I go back to Singapore, and she go back to Texas. And now what I do is I toss my coin. I see that I get a heads, and just by knowing that I get a head, I would know that she would be getting a tails, for example. The idea is that without her performing the experiment, I would be able to determine what the result of her experiment would be. There's a correlation between these two. There is not a relationship. It's something that's very important. These coins are not talking to each other. Rashmi and I are not talking to each other. But there's some correlation that helps me determine what would be the experimental result on the other side. This is the idea of quantum entanglement. So why are we discussing superposition and entanglement? When you want to make real-world applications of quantum computing, you want to write down quantum software. So how do we start? We want to use 2 principles. One is superposition, and the other one is entanglement. What they provide is something called parallelism. So, for example, you want to search a space. You can do with a classical computer. At one time, you could say one particular part of the space, right? But in quantum computing, you have this parallelism where you can do multiple things parallelly. Just like superposition, right? So now what we want to do is we want to leverage these 2 principles to be able to design and implement quantum algorithms to actually make it helpful for human beings, right? So that is exactly what we'll be talking about, how we can do with Classiq. So when you see the quantum stack, of course, we start with the lower level, which is the hardware always. So we have providers like AWS, who are also our collaborators. We have IonQ, who gives you the ion-trapped quantum computer, a special type of quantum computer. IBM gives you a superconductive quantum computer. And we have also Microsoft and many other providers. So what Classiq does for you is that you would be able to write programs in Python, and you would be able to abstract out the control and hardware layers. So what is this control layer in between? You might be confused. Control is basically the idea of me being able to talk to the hardware. So if you want to execute a program on a classical computer, you want to talk to the hardware, right? It's very similarly in the quantum stack as well. What Classiq does is we abstract out the need for you to understand control as well as hardware, and you can write the program and execute on an AWS quantum computer. You could do that on an IonQ quantum computer or an IBM or a Microsoft one. So that is the higher level picture here. Okay, so just like you have seen, algorithms in Python, C, C++, Java, we have a categorization here. So when you talk about high-level languages, we have Python, Java. When you talk about low-level languages, we have C, C++, assembly. So for example, in C++, what happens, you are able to manipulate the memory. And if you go a level down into assembly, you're able to play with registers, which is another level low to memory. But when you're working with Python, Python does the job for you. Your only job is to write down your mathematical equation that you want to do, or you want to do some scientific operation, or just write down a simple algorithm. So that is the high level difference between these two. And something very similar exists in quantum algorithms development as well. So when you see there are two levels of thinking, one is the lower level where you think about gates. So you have a set of qubits, you want to apply some gate operations, and you build a circuit out of it, right? So on the higher level, what we think is we design an algorithm, we write functions. And can you imagine that the small function I see on the right side, which is written in Classiq, is the equivalent to the one you see in the left. This is how we can show the complexity of quantum software. And that is why it's very important to think at a higher level. So let's see some interesting example from QIP. I'm sure you guys are high school students who are looking forward to some opportunities to learn more about quantum computing. I suggest that all of you, try to attend conferences or either read papers that are published in conferences like QIP. It's one of the leading ones here. So this is from 2024, this year. And they show in this paper how a particular Groover's algorithm will look like when you scale up to more qubits. So you can see if you would want to write this down by yourself, how difficult it would be. And that is why in Classiq, what we do is we write functions instead of operating at the gate levels. So what does Classiq do? Classiq is a quantum software tool. We do 4 things for you. We help you design your quantum algorithm. You can also optimize them. This is done in case of specific applications. Thirdly, you can analyze how your quantum program looks, what is the intricacies within the program, as well as execute them, of course, at the end. So what we'll do now, before we go to a short demo, will be to see the 2 components of Classiq. Firstly, we have a graphical user interface, a platform, and we have our own model, Q model language. So this is something that you might want to learn, but one very interesting thing is that just knowing Python is enough to use Classiq. So how do these 2 come together is what we're going to see now. So you might want to write your code in Python on a Jupyter notebook from VS Code or a Google Colab notebook, for example. And we have an API call here. So we have something called the show quantum program. This is the quantum program that you have written. And show is a program that helps you go and call the Classiq platform interface so that you can execute your program on the platform, right? So let's get started with a short demo. As of now, just feel free to look at the demo and try to familiarize yourself. And then we'll go on to the hands-on session where you will have an opportunity to do it on your own as well, right? So I'm sure you can see my screen.
Yeah, Nithyasri, just very quickly, we have some Google Colab files where we have done some initial coding, like a very simple hello world kind of a program. And then we do have a Google Colab file that the students now have access to, the Deutsche user, the Deutsche algorithms, Simon and Bernstein in there. If you could, as part of this, I don't know if it's planned for as part of this demo, but we could actually work with some of those files also to pull it into the Classiq platform through the students' accounts.
Sure.
And to show them how those programs would be now imported, actually exported in and be able to run that from
Sure,
this
absolutely.
Okay,
sure. Yeah.
I can. Would you like me to send you a link over chat to the Google Colab file?
Sure. Would it just be the Deutsche user algorithm? I can definitely show them after this demo how we do it in Classiq as well. Yeah.
Okay.
All right. Yeah. So let's get started with a very simple demo here. We're trying to work with preparing an initial state, which is the plus state. Okay, so let's first install Classiq. So you just do that with a pip install -u Classiq, and -u is essentially used when you have too many kernels, and it's a good practice in software engineering. So you would want to do it, install it with the -u. Right. So so I've already downloaded Classiq, so I have my requirements already satisfied. And pip show Classiq would help you see the version of Classiq. So this is the latest version that we'll be working on. And so now I told you that I want to be able to interface with an API to be able to go to the Classiq platform, right? So that's where this authenticate comes in. So it's a very simple process where you can run the cell classiq.authenticate, and it would give you a link that you can go in and confirm. So let's just quickly show that. Yes, and we'll all be all good. Okay. Wait a minute. Sure. This is because I have already authenticated myself, but let's quickly correct that. Okay.
So I guess this is a file you have posted on Slack as well. That's
no,
right.
This is just a demo file for them. The hands-on workshop is the one that I've shared with on Slack.
Oh, okay. So right now you're just doing the demo file, and then once you're done with this, then we have a chance to work with the other file, right?
Absolutely, that's right.
Okay.
That's right.
Okay.
Yeah.
Okay. Right.
So let's now try to get started on preparing an initial state, which is one of the most important parts of a quantum program. So a plus state looks essentially something like this. So it's a superposition of the 0 and 1 states, and we start with a 0 qubit. So how do we go from a 0 qubit to this guy, right? So this is essentially putting a qubit into superposition, right? So you would want to use the Hadamard gate. The Hadamard operation is what I apply here. Let's now start with the basics of how to write a function in Classiq. So we always start a Classiq function with an @q_func. So this is called a Python decorator, which is a good practice in software engineering in general. So this would be something that you would use every time you write a function in Classiq. So now let's say I want to prepare a plus state in this function. I have a qubit. Qubit is the variable that we use, the data type that we use in Classiq for a qubit, and my qubit would be named X, right? So now I want to apply the Hadamard gate on to my qubit X. So now let's run that. And whenever you write programs in Classiq, you always want to encapsulate your functions within a main function, as you do when you're classical programming as well. So that's exactly what we'll be doing here as well. And the qfunc would also be there for main program. So here we want a output type qubit. So you can see that this is the data type that we use in Classiq for an output qubit. And again, this is named X. Now we want to work with just one qubit, right? So we want to initialize it. And how do we initialize in Classiq? We use the allocate function. So I'm allocating one qubit and I want to name it X, right? So now we want to call this particular prepare plus state function on X to prepare the plus state. Let's go ahead and run that. Okay, so now, okay, great. So we've designed the program. So how do we want to, build a model and get it back into the Classiq platform, right? So what we want to do is we use the create model of the main. So we create the model of the main program, main function that we've written, and then we synthesize the quantum model that we've built, right? So this is basically what helps you contact the Classiq API. And finally, we want to do a show of quantum program, which takes us to the platform. So let's quickly run that. Okay.
So Nithyasri, can you explain a little bit more about the synthesize? I guess it calls the Classiq API. However,
right.
I guess, is this where the circuit is built based on the code that has been written?
That is right. Absolutely.
Okay.
Yes, it synthesizes the model into a quantum program, which can be then run on the Classiq platform.
Okay.
Yes. Okay, so let's quickly click on the platform. Okay, hope you can see my screen now. Okay, let me show you how you can also log in. So the best way to work with Classiq is to sign up with your Google account. I highly recommend that. All right, so I already have an account, so it's simpler for me, but it's just going to be as simple as this for you. Okay, so let's run. Share tab, okay. Right, so our program is being synthesized here in the platform. And right, you can see that you started with a 0 qubit, and you can see the program that you've written here. Let's expand and analyze the program. So I have my prepare plus state that I've written here. And what should you find inside? You should find the Hadamard gate, right? So you'll find Hadamard gate. All right, so let's execute this now. Let's say I want to execute with the Classiq simulator. One thing that I want to talk to you about here, because you've already run on an IBM quantum computer, this is something that we offer as well. You can run on a real IBM quantum computer, Microsoft's quantum computer, on AWS, IonQ, Google, and Alice and Bob. So what's special about a simulation, a quantum simulation versus running on a real quantum hardware, something that I want to point out to all of you. Basically, quantum simulation is a prototype for quantum computing. This is because our hardware, our quantum hardware, would not be called perfect at this point in time. Of course, as I mentioned, this is a very young field. It's very developing. And there are problems like quantum errors that rise up, and we have certain protocols like quantum error correction that we do apply, but it's still a very, very young field. So we prefer quantum simulation over, actually running on a quantum computer, so that we can a priori determine how we would be running on a real quantum computer before. So let's say I want to run this program for 1,000 times. You can think of it as tossing your coin for 1,000 times and see how many times a heads or a tails comes up. The only difference is that you would see whether it's a 1 or a 0. So let's just name this plus state and run it. All right, so now you'll be able to see the results. Let's see, so X is in the 0 state for 514 times, and X is in the 1 state for 486 times. So this is exactly how you can think of it. You can think of it like you're tossing a coin and seeing how many times each of these comes when you run for 1,000 times. Or it's not just that you can run 1,000 times. You can maybe, it could be a number greater than 1,000 to 20, 48 is also a good number to run. But 1,000 is generally a good number to see the probabilities. So let's switch back to the screen. Yeah, can you see my screen?
Yeah. Yeah, now we can, yes.
All right, that's good. So one other thing that I wanted to show you is how you can work with QMod itself. So of course, I showed you that we can work with Python, but also we have a native language called QMod, which we can use as well. So how we use it is by write QMod. This is a function that basically downloads the .qmod file into your system in the name that you want to give. So let's say we run this program, and we would be able to see it in our folder here. So we have, yeah. So what we could do here is we could download this file and go back to our platform, go to model, and upload your model. So this is something that you might want to do if you are more comfortable with QMod than Python. So then this will be a straightforward process where you again synthesize and execute your program. Okay. So now we're over with the demo. And if you noticed, what we did was we designed a program. We have not optimized yet, so we'll come back to that. We have analyzed our quantum programs, our quantum algorithm, and then we finally execute it with Classiq. So now one thing that we want to cover is we want to optimize. So generally, when you want to have a certain constraint on the number of qubits, for example, be it the width of the circuit or the depth of the circuit, you want to use this particular right tab that you have here. So you can choose your optimization parameter. It could be width or depth. Let's say we want to optimize for depth, and we want a maximum width of, let's say, 10 qubits, for example. And then you could go on to synthesize your model again. So this is how we could optimize from within the platform. But there's also another way to do this from the SDK as well, if you're more comfortable with Python. So I'll be showing you that in the more hands-on session that we'll have in just a few minutes, right? So, all right, so we designed, we optimized, we analyzed, and we executed programs with Classiq. So we're now back to the exciting part. Yeah.
So Nithyasri, just a quick question. So I guess what you're saying is you don't necessarily need to go change your code again to say you want to scale it from 2 qubits to 100 qubits. You could do that from inside the platform by writing code in a way that the number of qubits becomes a variable, right? That's what you're saying with the change in the width? Is that right? Did I get that correct?
More or less, but it's generally done when we are, having specific applications that restrict you on the number of qubits or the width or the depth of the circuit. So, for example, in pharma applications, for example, in protein folding, and maybe you want to run on, for example, there's an interesting challenge from Fujitsu recently, and they say that you want to run only with 40 qubits, for example, as a width. So that's one of the examples of where you want to do the optimization. Yeah.
Okay.
Yeah. Right. So now we are, come to the more exciting part of things. We'll be doing some hands-on work. So I hope all of you have received my Jupyter notebook. So please, open that up and feel free to, get started by signing up on the platform. So I'll give you a couple of minutes for that. And please let me know if you have any questions until now, and also if you have any issues with the logging in or installing the package. And please feel free to use either VS Code or Google Colab. Both will be fine. But please, while using Python 12, it's not compatible as such. So feel to use 3.11 or lesser versions.
I actually took the notebook link from Slack that you had posted. I've opened it on Google Colab and running the install from there. Just in case the students are wanting to know the exact steps. Anyone that hasn't found the Jupyter notebook that was posted on Slack?
I can send it back to them on the chat as well. Okay, so.
Oh, okay, I was just going to do that. Yeah, are you putting the link to chat? Okay, I can go ahead and do that.
Yeah, sure. Thank you.
Okay, and this can be opened up in the Google Colab and run from there. Since we've done that before in class, I guess students are aware of how to use it.
Excellent.
So I got some errors here on my run.
Yes, please feel free to share.
Yeah, it says PIP's dependency resolver does not currently take into account all the packages that are installed. It's referring to something Torch 2.3.0 plus CU121 requires NVIDIA.
Is it something like this?
Yes.
Do you see something like this? Yeah, yes. Don't worry about that. Don't worry about that.
Okay, so just ignore those.
As long as you have it successfully installed, it should be completely all right. Yeah.
Oh, so okay. Let me check. Yeah, it did successfully install. Yes.
Yeah, you're all good.
Is anyone else ready with the install or has seen this output?
Does anybody need any help with the installation and the sign up? Please let me know. All right, if nobody has a problem with the installation, I think we can get started with the session. So the first thing that we want to do here is the authentication process. I'm doing this additional step because I've already had my authentication done, but you might want to avoid this step. So the difference between working on a Google Colab notebook as well as your VS Code is that on a VS Code, you just do this authentication once because this is done locally on your PC. Whereas when you're working with a Google Colab notebook, you have to do it for each of your Google Colab notebooks, right? So yeah, let's just do that quickly.
So I guess when I run that authenticate,
yes,
it is giving me, it gives me a new browser page with my, so it's giving me a user code. And then it says if a browser doesn't automatically open, please visit this URL.
Yes, that's right. You can go ahead and click on it and click confirm. So one difference between, again, VS Code and Google Colab is that when you have your VS Code, it automatically opens up the URL for you. Whereas in Google Colab, you have to do that. Yeah.
Okay.
Yes. Right, so let's go ahead and import our sub-packages in the SDK. Are all of you on track? Do you want me to slow down or how's the?
I think just give us a few minutes.
Sure.
Some folks are having some issues. Let me just check.
Please let me know. I'd be happy to help.
So I see, Kabir, you said whenever I try to sign up, it says something went wrong. Okay, Linda, just very quickly, you can open a new Colab file. Okay, so I think you kind of got it. So Kabir, when you try to sign up, did you create an account on the Classiq platform before, or you're just trying to sign up right now?
Is he a new member or is he already logged in?
Let me just check.
Sure. I think one thing that you can try is to sign. Sorry.
So I guess I just want to clarify. Everyone needs an account. Sign up for an account in Classiq.
Yes.
And then they're running the authenticate. They're given a user code, and then they have to log in using the user ID and password that they had set up when they signed up for the platform, right?
Absolutely. So there are two parts to it. One is to authenticate yourself on the Google Colab, and other is to separately go on classiq.platform.io and sign up. And the best way to do that would be through your Google account.
Okay. Kabir, are you able to sign up? Or I was here, but I missed a few, like 2 weeks, so it might have been there that you went to. Yeah, we do need to sign up for that account. Let me. Let me re-forward the email with some information.
Here the link as well. So it's platform.classiq.io.
Yeah, platform.classiq.io. That's right. Kabir, are you receiving emails on your utdallas.edu email address?
Was he able to sign up?
Actually, let me just see something else.
Sure. Is there any error that's coming up that I can help with?
Yeah, I'm just forwarding him his this email that would kind of guide him how to sign up.
All right, sure.
But the thing is, it's going to his UT Dallas. Apparently, I don't have his other email address. Let me.
Right. I think you can feel free to put the website on the chat. I think I don't have access to the chat, but just Classiq.
Oh, is that right? Okay, hang on. Let me just add it.
Yeah. Sure. So you can just put in platform.classiq.io.
Okay, he's got some Classiq. Oops, something went wrong. Callback URL mismatch. The provided redirect URI is not listed. The list of allowed callback URLs.
Was it platform.classiq.io that he tried?
So I think this is from his authenticate.
All right. The way to approach this is to first sign up your account on platform.classiq.io, and then you go on the Google Colab, so that you would be able to log in within your account from the Python Jupyter notebook we have. Yeah. Can I check if he did the sign up first and then the authenticate after that?
So, Nithyasri, I just made you the attendee. I think you turning up as guest earlier?
I think that's right.
Yeah. Do you see the chat now?
I don't.
Okay, I think he. So you got. So Kabir, can you confirm you got an account set up on platform.classiq.io? And now when you run the authenticate with that user ID password that you're able to connect to the Classiq platform from either the Google Colab that you're running or in whatever format you're running that code, the Jupyter Notebook? Okay, yes, he said yes. Okay.
Fantastic. Fantastic.
Anyone having any trouble? I mean, we will be in class tomorrow on campus. We can run through some of these things again one more time tomorrow, or reach out to me over email and we can set up some time to walk you through some of this stuff.
Absolutely. I'll be happy to do that. Rashmi, I think I'm not able to share my screen now.
Oh, you're not even discussing? Okay. I think I...
That's right, yeah. It says only organizers can present.
Okay.
That's right.
Make a presenter.
Okay, great, awesome. So anyway, back up. Happy that Kabir could log in as well. So let's get started with our hands-on session. Right, so the first example that we want to see is how to prepare a minus state. So we saw how we can prepare a plus state, which is slightly more simpler. So now what we want to do is we want to go from a 0 qubit to a qubit that is in superposition of this minus state. So how would we want to do this? So we see that we start with the decorator as always. We write prepare minus state, and we want to have one qubit. We want to have a qubit type data type, and let's just name him X, right? So what do you want to do here? So a good way of understanding what the 0 and 1 qubits are through matrices. So you can write down them mathematically and try to come from 0 to 1 over root 2, 0 minus 1. So that's the best way to understand how we're writing this code, right? So let me show you now the solution for this. Firstly, we want to apply the X gate. So this is the poly X gate that we want to apply on the X qubit and followed by the Hadamard. So let's quickly run this. And as is customary, we want to write a main function now. So here, of course, we are working with still just one qubit, which is going to be the output. And we allocate one qubit, which is X. And now we want to call this function, right? So what we do, we say prepare minus state on X. So let's quickly run that. And then we go on to build a quantum model using the create model, and we feed in the main function that we've written here. And now we want to synthesize this quantum model into a quantum program. And then finally, we use the show of quantum program to execute this on the Classiq platform. All right, synthesizing. Okay, so now you can see we started off with a 0 qubit and we see the program. Let's analyze it. We see a prepare minus state function that we wrote. And when you go in, we see the X gate and the Hadamard gate. So let's quickly execute it again. Let's use the Classiq simulator again to execute. Let's say I want to run it for 1,000 times again. Always remember the coin toss experiment. So let's say I want to say minus state and I run it. So now again, we want to see how many times 0 and how many times 1 occur for these 1,000 times. So if you see here, you can see X is 0, the state 0 occurs for 502 times, whereas you can see that the 1 state occurs for 498 times. So this is how you can analyze with the Classiq platform the results that you get. So let me give you quickly a minute to do this on your own. And then we'll go on to the next example where you would have, you would be doing it, and I wouldn't be giving the solution as easily as I give this one. So let's have you guys quickly try to execute this, and I can share the solutions with you as well on the Slack channel, right? So let me do that.
Just a quick observation. When I try to, I think I'm on a Mac, and when I'm running the Google Colab on here, obviously it tries to open that URL on Safari. I guess if the URL in Safari doesn't come up very well. So I've been using Chrome to sign up for the platform and kind of go to the platform. So if anyone is not seeing something come up in the browser, I guess Classiq works better on some of the tested browsers like Chrome and Firefox. Is that right? Because it looks like Safari is not a compatible.
It is, but it has a slightly different procedure. But feel free to use Google Chrome for the best results. And thanks for bringing up that point, Rashmi.
So yeah, I just took that URL and copied and pasted it into my Chrome so that I could see the circuit synthesis and all that stuff happening. Yeah.
Absolutely. Yeah. All right. So were all of you able to execute this and see your measurement results? You could drop maybe a like on the solution, for example, if you were able to execute it. So that'll be a good indication that you're following, right, on Slack.
So Nithyasri, could you go back to that URL?
Yeah.
What should we be seeing at the URL when it opens that up? What does it show for you when you get back there?
So when you click on here, you're supposed to see the Classiq platform synthesizing your program, and you would see something like this. Yeah.
All right. Okay.
Yeah. All right. So were you guys able to execute this program and see your results with your own eyes? And just let me know. Okay, I see some likes. Fantastic. So let's move on to the next example now. Feel free to stop me if you have any questions in between and if you're having any troubles with the code. So I'll be happy to help. Okay, so next we'll be doing something.
Just one second. I think Agniv, you said that when you run it, it's asking for credentials. Have you signed up on the platform?
Sure, I can help him with that. I think it's because he's trying to run on a IBM quantum computer, for example. So what we could do here is when you are in your execute tab, for example, let me quickly show you. When you're in the execute tab, feel free to change the vendor to Classiq. It'll be the easiest one for you to for this session. So you'll be executing on the Classiq simulator, and you could just say simulator and click off your hardware and save vector simulators. And then if you run, you shouldn't face this issue. Do I have my, my vendor is Classiq. Okay, now you shouldn't. Yeah. So just make sure to choose Classiq as your only vendor in the particular tab that I showed you, the execution, and it should be all good. Was he able to run now, Rashmi?
Let me just check. Okay. Hi, Agniv, can you post in the chat? Are you able to run it when you select Classiq? Yes, he says yes. Yes.
Okay, great. So now we can move on to another interesting thing that we talked about theoretically, which is superposition. So we're going to write a function that we want to create an initial state with. So what we want to do with that initial state is that we want to have a number of qubits, and we want to put each of them into an equal superposition, right? So what we want to do here is we want to work with a quantum array of qubits, and let's call that guy register. So how would we want to go ahead and do this? We have one hint here, which is to use the apply to all. right? So the apply to all function is where you can give in a gate and the target qubit on which you want to apply this operand. So let me know what gate that you want to be applying it on. The target, of course, is reg. I will give that to you. But what is the gate operand that we want to use to put the qubits into superposition? Any answers? And don't feel shy at all, guys. Please feel free to open up your mics. Any answers?
No, not in the chat just as yet.
All right. Guys, no answer is wrong. Just give it a try. So what is a qubit that, what is the gate that we use to put a qubit into superposition? We saw this in the plus state.
Yes, I have a response from Kabir. He says H gate, the Hadamard gate.
Fantastic. You're right, Kabir. Yes, it is the Hadamard gate. So here, what we do is we use the apply all function, and our gate operand would be H, the Hadamard gate that we want to apply on our register. So let's run that now. Okay, great. So now that we have run this particular create initial function, initial state function, we want to write a main function now to encapsulate this function with it, to be able to synthesize a model and a program. So here, what we want to do, we want to allocate this register with a few qubits, right? So now we are not just dealing with one qubit. So it's not just allocate of one, but let's say we want to do it with 4 qubits. How would you write that? This is what we would do. So we have a output, which is a quantum array, and we want to allocate 4 qubits, and they would be called the register. So the register is the array of these 4 qubits. And then you call the function create initial state with register as the argument. So let's run that. Great. So now, how do you show the quantum program in your API? So we saw this again. This would be the show of quantum program, right? So what we do is we first synthesize the model. So here, this is a shorthand form of doing this. So if you see up here, you would see something like this, right? So this particular 2 lines of code can be written as just 1 line, where you want to encapsulate your create model main and synthesize in the same line. So that's just a way of writing it. So now we'll say show of this quantum program qprop. And now you should get a link like this. We click in and go into the platform. Let's execute and analyze how this program looks as well. So here you should see 4 qubits. And we would start with each of them in the 0 state, right? So that's exactly what we see here. We have 4 qubits each in the 0 state. And we have the program. Let's analyze it. So you see the create initial state function as you keep expanding the program. You see the circuit that you've built. What would be inside the circuit? Yeah, all of these qubits have been applied with the Hadamard gate to put them in equal superposition. Let's now execute it. Again, we want to execute with Classiq as the vendor and just on the simulator, again for 1,000 times, for example. And let's say, we want to say initial state for this, initial state, and click on run. Again, here, something that's going to be different is that you have, you're working with 4 qubits. So you always need to remember this number 2 to the power n. So you have to do 2 to the power 4, which gives you 16 outcomes. So here in these 16 outcomes, what you would see is that you will see the state 0000, 0001, all the way up to 1110 and 1111. And each of the times that each of these guys occur for these sample space of 1,000 times. So here, for example, the register number 15. So when register is 15, you have the 111 state, which is occurring for 66 times out of the 1,000 times. And when you see, for example, 0011, it occurs for 77 times, the register is equal to 3. So this is how you can analyze your measurement outcomes for this particular program. So just let me know if you were able to run this as well. And then we can go on to the more advanced parts of arithmetics in Classiq.
I got an error when I was trying to synthesize.
Yep.
I'm not sure why it says trace back most recent call last. It's giving me a name error.
All right. Could you maybe I can share the solution with you and you could try it out because maybe you did you execute all the cells?
Yeah, I did. Yeah, I think up until now, yeah, I mean, I did execute all the cells. It worked on the last one when I did the synthesize in the show quantum program.
Right.
The first,
maybe
the first example you had given. Then on the uniform superposition, I could create the initial state, but when I run the synthesize, create model main.
Over here? Yes, over here, right?
Can
you confirm whether you have
I'm missing, I'm missing this in between. Right. I'm not sure why I'm missing this again.
Yeah, because this was, for an exercise for them to try out as well. So I haven't given them the solutions yet. Yeah. So I can put that very quickly in the chat.
Okay, I think we are missing this piece. Okay, yes, okay.
That's right, yeah. It was meant to be an exercise for yeah. So let me quickly share. And again, feel free when you are able to run this, you can just give a thumbs up there.
Oh, you posted it on the Slack, right?
That's right, yeah. Okay, so this is the solution for the uniform superposition. Yeah. And let me know if you're facing any problems, and also let me know if you're able to run correctly. Right, anyone was able to execute this successfully?
Oh yeah, now it's working, yes.
Okay, great. Any others who could do this? Right, I see one person, awesome. Any others? Okay, great. It's building up. Good. That's good. So I think we can move on to the next part of the hands-on workshop, which would be to do some arithmetic operations with Classiq. So just like you work with a classical computer, you might want to see how, for example, you want to evaluate a function, a linear function like y is equal to x squared plus 1, right? So that's exactly what we're going to see how to do with quantum arithmetic. So here, let's say we want to start off with the 4 qubits. I'll talk about these two in just a while, but here what we do is we are trying to build just a main function here with the decorator q func. We have x and y, which would be our output values, right? So for this particular equation, we want to see what values of x and y we could get. So here, what we do is we don't allocate qubits. We are allocating quantum numbers. So if you see x and y, they are of the type quantum numbers. And because they're outputs, they say, it's output of quantum numbers, right? So here, allocate num is the function that allows you to initialize numbers, right? So that's exactly what we have with x and y, right? So that's exactly what we're doing here. So here we say the number of qubits that I want to use for this particular operation is num qubits, which is 4 qubits. And then is signed to something that allows you to say whether you want plus or minus integer values of x and y. So is signed is true here, which means that x and y could be of negative, x here could be of a negative value. And then we have fractional digits. As I don't want to complicate, let's say I don't want any fractional digits in this particular function, and then the output, the x would be the out. Right. So then the first thing that we want to do here is to put the x in a superposition, right, of all the possible states that it can be in, and all the possible states in a very particular domain. The domain would be from negative 2 over 2 to the power n, all the way up to 2 to the power n minus 1. So this is the domain that we are working with for sine numbers, right? So what we do next is to write down the equation that we want to explore, that we want to evaluate. Finally, we create a quantum model. So let's run this. Okay, so once we've created the model, we want to synthesize this Q mod and finally view it. All right, so we see it synthesizing. Yes. So something very interesting here is that we said that we want to work only with 4 qubits, but we see some more of them, right? Why do we have them? Let's see in a minute. So when you explore into the program, you see the allocate num. This is being applied only on the 4 qubits that we wanted to work with. Secondly, we have the Hadamard transform, which puts all of these qubits into a uniform superposition. Again, something that is being applied only on the 4 qubits that we are working on. So what are these additional qubits? These are called auxiliary qubits, which help with our arithmetic operations. So we have a power and we have an adder, right? So we have an x square and then a sum, a plus 1, an adder. So when you go into the arithmetic, you can see that there's a power and then there's an adder. And let's just see this. This is fun. So imagine having to write down the power as gates. This is exactly what you would want to think up in your mind to be able to execute this on, for example, anything except Classiq. So if you want to work with gate level softwares, you want to be able to write down each of these gates by yourself. That is exactly what Classiq abstracts out for you. So this is the slide that I showed you. Let's go back quickly to that slide to show you the difference. Yes, so this is exactly what we're doing here. So imagine having to write your power as gates, as so many of these gates, and having to just write a function. So that is exactly what Classiq does for you. All right, so let's go back where all of you able to explore and execute this program.
So there's a question with Siddharth here. He says, why do we need to create a superposition in the domain of minus 2 to the power n to 2 to the power n minus 1?
Yes, that's a good question. So basically, our idea is to create a superposition of every possible state that the x can be in. So when you're working with 4 qubits and for a sine number, you have the equation. This is a mathematically known fact that you want to work with minus 2 to the power n. From minus 2 to the power n to 2 to the power n minus 1. So this is basically because we are using sine numbers. And secondly, because we want to have the superposition of every possible state for that qubit. Yeah. Does that answer your question?
Yeah, he says yes.
Okay, great. So were you guys able to execute this piece of code and are able to see the results?
I got a response from Linda, Kabir, and Akshad. They say yes.
Okay, great. So let's move on to something slightly advanced, arithmetic. So now we were working with y is equal to x squared plus 1, right? So let's add in a little bit more complexity to this with more integers, more classical integers. So let's say we want to do y is equal to ax plus 1 and try to evaluate. So what's complex about this is that you want to fix a and b, two quantum numbers, with some constant classical integers, right? So let's see how we can do this. So here, you might want to comment out this particular line of code in your Google Colab. This is basically the deprecated version of Classiq's way of writing a constant integer, constant classical integer. So what we would want to use here is a C int instead of a Q parameter, right? So this is something to note. So here what I do is I start with writing a linear function. Yeah, is there a question? Is there a question, Rashmi?
No.
Okay, sure. So I can continue. So in the linear function, what we want to do is we want to work with a and b, which are classical integers, and which would be constants, right? And then we want to work with x and y, where y is going to be our output, which is the output, which is of type quantum number, and we have x, which is also a quantum number. So let's run this. So we can see that the equation that we want to evaluate is written here. Don't bother about this. This just means equality, right? Okay. So now what we go ahead and do is write the main function. So we want to see how the x and y values go, right? So we want them both to be output quantum numbers. And let's say I want to fix my a and b to these values. These can be any values that you want to go with. But let's just say a is 2 and b is 1. Now I want to allocate my numbers, right? So let's say again, I want to work with 4 qubits, but this time, let me switch things around. Let's say I don't want signed numbers. So what this means is that you would not be able to see negative numbers for x, negative values for x. And again, here, for the sake of simplicity, let's have fractional digits as 0, which means no fractional digits, and then out would be x. Again, here, what we do is the similar process that we saw in the previous example, where we put the x into superposition of all possible states. Finally, we call our linear function with a, b as 2 and 1, and we have the x and y, which are our output quantum numbers. Finally, we go on to create a model using the main function. Let's quickly do that. And then we synthesize a model into a quantum program. So let's again switch things a little bit here. Let's say you're more comfortable with working with Python, the SDK, rather than the platform. Guess what? You can execute and also analyze your circuit, your quantum program within the SDK without even going into the platform. So let's see how you can do that. So for executing of a quantum program, you just have to simply call execute on your QProg, which is your quantum program that you built before on the model. And let's say we give it the name job. Right. So let's run that quickly. Yeah.
Can I just interrupt you a little bit? Can you go back to the deprecated line of code?
What was
sure. New line of code? Could you post that on the Slack channel?
Absolutely. Yeah. It's basically the quantum parameter integer has been now changed to C8. The classical integer.
Yeah.
Let me just quickly. Yeah. All right. Okay, so this would be the function that you want to replace it with. This particular data type is what you want to replace for quantum parameter integer. All right. So yes. So finally, we have executed this quantum program within the SDK itself. So now let's see how we can analyze it within the SDK as well. So this can be done by calling on your job, which is the execution of the quantum program, dot result. And then this is just a nice way of presenting. So just to parse the output and show it in a very nice way, we do this particular operation. Let's quickly run it. And as we had given before, that is sign is going to be false. You will not be able to see any negative numbers, negative inputs for x. So we can see the values for each x, what would be your y value as well. So this is how we can run from directly within the SDK if you feel more comfortable with Python. Were all of you guys able to run this?
Just waiting on responses to see if everyone is up to this point. I hope everyone got that a new line of code for the deprecated line of code. Okay. Yeah, Linda says yes.
Wait. So all good?
Akshat says has worked as well.
Great. Awesome. So let's now go on to see how we can optimize for example, with the parameter of width from within the SDK. So I showed you within the platform how you can optimize over here, right? So we can choose the optimization parameter and then choose the maximum width or maximum depth. So how can we do this from within the SDK itself, right? So this is how we can do it. We have already built a quantum model here for this particular arithmetic expression. So we have a Q mod. So what we will do is we will want to build upon this Q mod, but with certain constraints. How do we do that? Let's say we want to give it the name quantum model with constraints. And then we use the set constraints function. We pass in first the quantum model that we already have built without any constraints, and followed by the constraints that you want to give. So within the constraints, what you want to give is the parameter which you want to use for the optimization, and two, maximum depth or maximum width. So let's say I'm optimizing for width here. So let's say my optimization parameter would be width, and my maximum depth would be up to 500 qubits. So let's run this. And then we want to synthesize this particular new model that has constraints now, just simply by using the synthesize of quantum model with constraints. And then you could use this particular syntax. So here, to find the circuit's width, you call the class quantum program, and you feed in the quantum program that you've built with the new model and say .data.width. This gives you the width of the circuit. Similarly, for depth, what we would do is transpiled circuit here just means that it is being changed. So it's been optimized. So here for depth, what we would do, this is being transpiled because this is not the optimization parameter that we started with. So for depth, you would say transpile circuit and then call depth. Finally, you can put it out like this. So this is being done just from your SDK, and this is mainly for people who feel more comfortable with Python rather than a GUI, which is in the case of me, I'm very comfortable with Python than a GUI. So I think people like that would appreciate this. Hope all of you were able to try out optimizing within the SDK. Just let me know.
So Nithyasri, could you, would you be able to post this Jupyter file, the one that you're working with right now with this optimization? I think the current one doesn't have it, right?
It does. All right, but sure, I can post it for you. We'll also be posting the entire solutions Jupyter notebook after the session as well, so don't worry about it. And let me post this for you now for optimization.
Yeah, I think that's what some of the students are saying, that they don't see optimization. So yeah, if you could just add it there, or once we are done with the session, if you could give us this final Jupyter notebook.
Absolutely will, yeah. So let me please share on the chat as well.
So Siddharth, that specific code is deprecated. If you go to the Slack channel, Texas, did you join the Slack channel? If you go to the Slack channel, Nithyasri has posted the deprecated line of code, which is QParam will not work. You'll have to use cint.
Cint, absolutely.
And I thank you, Akshaj. So Texas channel. Okay, hang on. You could search. I think it doesn't show up on the list, but you will need to search inside Slack for this channel.
Oh, that is right. The channel's name would
Texas workshop first session.
That's right.
Let me see if I can get in there and send an invite.
Sure.
Okay, I don't see.
Was he able to do this?
Just one sec.
Sure.
Okay. Yeah, he just joined. So Siddharth, if you go to that Slack channel and then look at the message that Nithyasri posted 10:53 a.m. Where she says it's a deprecated. Yeah. So you hashtag your def linear function, basically the one that has q param in it, and you replace that with a linear function with cint.
That's right.
Okay. So Linda, to your question, I think that code is now in the Slack channel. Okay, thank you, Nithyasri, for posting that. I just saw your message to Siddharth.
Yeah, no problem. No problem. Right. So, so all of you guys, were you also able to do the optimization from the SDK?
I think I am still getting an error on the optimization, but let me just try one more time.
Sure. What was the error that you got?
I think I have a syntax error somewhere.
Sure, you can share it with me.
Yeah, I think I got a syntax error on the code.
All right. So, did you use the Q mod from the previous arithmetic example, the quantum model that we built in the previous example?
Q mod, yeah. I think I have, yeah. Yeah, so quantum model constraints, set constraints, Q mod.
Yeah.
Let's see where the issue is. Line 1. Oh. Sorry.
Did you make sure to use the quantum model?
I know I had a syntax error. So I've got it.
All right.
The circuit width is 11 and circuit depth is 360. Yeah.
Yes, absolutely. Yeah. Okay, great. So I hope all of you were able to optimize from within the SDK. So now I would like to give you a fun take-home exercise. I'm sure on 22nd of July, my colleague Alexandre, he'll be talking to you more about Classiq, some advanced applications as well with you. So before that, this would be a very nice thing for you to try on your own at home. And this is just very similar to the linear function that we saw, but we are changing the domain as well as the values of A and B. So this has fractional digits. Try this out. It'll be a very nice example for all of you. And next will be a tutorial. This is also something I would like you to read up before you come up for the next session. And so this would be the end of the hands-on workshop, but I would like to show you something very exciting on the Classiq platform. So we want to show you some applications. So I talked to you about how this field is interdisciplinary, right? So we have applications in finance. Let's look into it. We have something called option pricing. These are related to stocks. We have a credit card fraud detection. This is something that's a serious problem that is something that's possible to solve with quantum computers. And we have problems in chemistry like protein folding or VQE, which are more advanced algorithms in quantum computing, logistics, and so many more. So for example, traveling salesman problem is something that I think you can relate with. So let's say you order pizza and the guy that's going to deliver to you has to go to 5 different places before he delivers to you. How fast and how efficient can he be able to do it is something that traveling salesman problem talks about. And this is something that can exploit the loss of quantum mechanics to do the computation faster. So one thing that I noticed that Rashmi asked me to talk about was also Zosa. Before that, I would like to show you something, which is an algorithm in Classiq. So there's an algorithm called the phase kickback, which is essentially a primitive in quantum computing that is used. It's a sub-algorithm, basically, that is used in various different advanced algorithms. So what happens here is basically that we have a function and we want to keep the phase of that particular function's result. So a phase change, right? So let's just see how this algorithm might look. I'm not going to go into the details, but just want to give you an idea of how a real algorithm in quantum computing would look like obviously. So this is something that you're familiar with. It would be a preparing of the state. You have already done this, preparing the minor state with the help of the X and H gates, right? So one thing that would be different here is to build the oracle function. So basically, the oracle function is where you want to. An oracle is basically a black box that you want to ask questions to. So for example, you want to ask a question that, let's say, is f of x is equal to 0, for example, or you want to check whether the quantum number x is 0 or not, and do operations based on that. That is where you can build a function like this, right? So you give basically a condition that the function should satisfy, and you ask the oracle that question. And here we use a advanced function called within apply, which basically means that you want to apply in certain cases unitary operations. So let's say you want to apply on a black box, you want to apply A and inverse of A, a sandwich of A and inverse of A. That is where within apply is used. And I wouldn't go too much into detail of this algorithm, but I just wanted to show you how phase kickback would look like. And then finally, you assimilate all of these guys into the main function, go on to create a model, synthesize as usual. So let's quickly go back to the platform, and I want to show you Deutsch-Zosa, which okay, so we have two examples here. One would be for a larger number, but let's go for the smaller example. Yeah, so here, let's say we are wanting to work with a condition in the oracle. So this also has an oracle. That's why I wanted to bring up the phase kickback, so you have an idea of how this would look like. So the question that we want to ask this particular oracle is whether x is greater than 7, for example, right? So here again, we start off with a preparation of a minor state. This is something again that you are familiar with, and of course this code might look a little bit different to you because this is QMod, this is not Python, but I think it helps to also teach you guys a little bit about how QMod works. So yeah, so allocate of 1 and comma output, the qubit would look something like this here. So you're assigning 1 qubit, and it would be the out qubit, right? So that is what this particular piece of code means. And then you go on into your oracle function, right? The oracle, this is slightly more complex, and this was something that my colleague also wanted to cover, but I want to give you a slight introduction so you'll be ready for that session. So here we feed in the predicate, and we use again the within apply because we want to have a sandwich of the predicate, right? So here we go on, we do certain things like putting the qubits into superposition, a uniform superposition. These are things that you've already seen, so I just want to reinforce that these are also used in the Deutsch-Zosa algorithm. Finally, again, here you want to encapsulate all of these, what I call the Deutsch-Zosa function. With lambda is basically used when you want to call a function within a function. This is something in Python, not just in quantum computing, in general in Python. And so this is how you would write the main function to execute a program which corresponds to the Deutsch-Zosa algorithm. So you could go on to the platform now and go to model and just type in Deutsch-Zosa and go to the small example. So please feel free to execute this program along with me. So let's just click synthesize. Program synthesizing. All right, so we're working with 10 qubits here, all the way from Q0 to Q9. And you can analyze this by going in deeper, by expanding. You could see the Hadamard transform that is happening as a sandwich. This is basically what within apply does for you. So you see a sandwich within the you see a sandwich of the oracle with the Hadamard transform, which puts the superposition of the qubits. And you can go in and see as well what happens with the oracle. You prepare a minor state here, like I showed, and some more complex things that happen are shown here. Right? So this is just something I wanted to show you quickly, but you can feel free to again execute this along with me. Let's say I want to again execute on the Classiq simulator. Let's name it DJ for Okay. And yes.
Yeah. So I guess
Okay.
my execution shows 13 qubits. I guess it's variable for everyone, right? Yours is 9 qubits. I can go
Yes,
back and
that is
look at the code. I think somewhere it's picking up a random number of qubits, right?
That is right. Also, because I applied optimization, I believe. That also changes the variables. But yes, yes. All right. So if you see here, you can see that you get a string of 1000 and your x is equal to 8. So basically in Deutsch-Zosa, your idea is to see whether a function is balanced or constant. So if it is constant, you want to see the same number of zeros and ones in that string. So the string 1000 on the top that you see is the string that we want to analyze into and see whether the function is either constant or balanced. So when it's balanced, you would, I think I said the opposite. So if it's going to be balanced, you want to see equal number of ones and zeros in the string. And if it's constant, you're just going to see, for example, 0000. So that is how we can look at the Deutsch-Zosa algorithm. Okay, so yes, I very highly recommend that you go through some of these built-in algorithms that we have and execute them with various different optimization parameters, play with the platform more to understand. We have some more like the Bernstein Vazirani, which is also a very important one, and Groover, of course. And we have, in addition to that, some tutorials that you can go through as well, starting from a hello world, how to do face clickback that I just showed you a couple of minutes ago. And finally, I would very, very highly recommend that you go through the applications because when you get into the workforce, of course, today you are high school students, tomorrow you'll be going to college, but finally you want to join the quantum workforce, right? So to be able to practically implement solutions, you would like to go here and understand what kind of subdomain you like. For example, someone might like finance more than chemistry and wants to build applications to solve problems in that field using quantum computing. So I very highly recommend that you go through some of these examples. All right, so going back to my slides. So we saw how to execute, how to design, to optimize, and analyze, and finally execute on the Classiq simulator. So I hope that all of you guys had a good practical session, gotten a good familiarity with Classiq platform and how to use the SDK. So I would like to thank all of you and the University of Texas for giving me this opportunity. Thanks to Rashmi and Professor J. Kesavan for organizing such a wonderful program. And feel free to reach out anytime regarding this code, the take-home exercise, or any other thing, even in general about quantum computing or Classiq. We'll be very happy to help you out. And finally, I'm opening up the stage for Q&A, so feel free to shoot out your questions.
Well, thank you so much, Nithyasri. This was a pretty intense, I think, session. But I think it has kind of broadened our perspective on by looking at a platform. I mean, we've run some programs in Qiskit, but this has now kind of broadened up our perspective on what all is possible in terms of building algorithms. But we will be going through, as far as the students are concerned, we'll be going through some of these things again tomorrow when we are on campus. I just want to make sure everyone has a good hold on the different aspects of how to run it, how to synthesize, how to execute, how to show the quantum programs. And then we will do a little bit of hands-on exploration, as you had suggested, looking at the different algorithms that are on there. We'll work through these. We might come to more questions. We'll post it on the Slack.
Absolutely.
And I think that was the purpose of the Slack, right? So that as we explore this further, we can ask those questions to you guys. The one question I have is the next session that we have next Monday. What would be covered as part of that advanced session? Do you know?
Yes, it would be mostly an application, focusing more on just one algorithm in quantum computing. But yes, it'll be slightly more advanced than this.
Yeah. Okay, got you. Okay. Yeah. So I have one question from Siddharth. He says, should we post the to-do exercises in Slack?
Yes, please feel free to do that.
Okay.
If you get the right solution, I'll be very happy to tell you that you're right. So awesome, that would be great. And of course, please feel free to contact me even outside of this session. Of course, now it's open for Q&A. But even if you want some help with, for example, I heard that you also have a quantum research project that you'll be working on after this program. Is that right?
Yeah, that's right. So we have a last week set up. I mean, this week and next week, I guess we will be on the Classiq platform exploring. We're going to go back to Shore's algorithm, Grover's algorithm. We're going to look at those algorithms on your platform as well. And then we have a final week where the students can actually now go build something that they want to, that they've kind of thought about. But obviously, a few more pieces have to come together before they get to that.
Yeah, absolutely. How cool is that? You guys are very lucky.
Yeah, you're absolutely right. I wish I had something like this when I was in high school.
Yes, well.
So this actually, in fact, I would say it would be nice for all the students to post their to-do exercise in Slack. Maybe it opens up an opportunity for them to go intern at Classiq at some point.
Absolutely.
Because now Classiq has access to all these students that have actually been on their platform, kind of understand what's going on, have some background on quantum mechanics, quantum computing. They have access to a bigger pool of people now that they can call in, during summer programs, or maybe select a few to talk about, what was their experience in the Classiq platform. So I would actually recommend all students interact with the Slack, go and leave at least some footprint on there that you've been there, you've done this. So that, again, and I was talking to Nithyasri before this training started, how we talk about history of classical computing. There are certain names burned into the history of classical computing. If you want your name to be burned into the history of quantum computing, you do want to go in and be part of these Slack communities, attend the conferences. Tomorrow you will realize where in the history you were here exactly at the inception, at the beginning. And this is truly a historical moment for everyone. I mean, everybody who's participating here is part of this history of quantum computing now. So in the future, 10 years from now, when students are studying quantum computing, I hope that some of these names are showing up because we were here first. So giving you a perspective of how important this is and what you guys are doing here. Any questions for Nithyasri based on the exercises? And no issues if you have not been able to follow through. We're going to, again, walk through it tomorrow on the campus. Just want to make sure every student has had a chance to try it. I know some are faster than the others, but I want to make sure everyone is caught up tomorrow when we are on campus. But any questions so far?
And feel free to ask any questions that you have, even in general about quantum computing. And I just want to share one thing with you, that 10 years down the line, I want to see at least one of you, not one, I want all of you guys to come approach me. And I have a coffee that I owe you if you are a quantum scientist or a professor at any of the universities in the world working on quantum computing. I owe you a coffee, all right?
That's a good way for it. Yeah, so go look for her. She's in Singapore right now. I mean, right now she's coming in from India.
That's right.
She's studying in Singapore. But you have a chance to go across the world to catch a coffee with her.
Absolutely.
Okay. So the other thing is, while students are looking at this recording later today, please post questions to the Slack. That's why that community has been built. Make sure you use the resource. And again, I want to put perspective to the students. It's not easy to come through these resources. I mean, it's very nice of Classiq to spend time with us. They're a very well-known company, very busy people. They're doing a lot of work in this space. And I'm very grateful that they've actually sent somebody, Nithyasri, and the next Monday, they're going to run an advanced training It's not easy to bring these resources to a summer workshop. But I'm very grateful to University of Texas Dallas, to Amazon, to Classiq, Nithyasri, Tali, everybody who's on the team, for taking the time out of the busy schedules to come and, do this for us. I know how tough it is, running. In fact, we were on calls with Israel, a few weeks, several weeks in a row, getting this program together. And, things are not easy over there in Israel right now. They were all working from home, and they were not very conducive environments outside their windows. It's really sad. But then, they've reached out to the entire team all over the world, Singapore, India, wherever it is, and they're trying to bring us folks that can train us here in America while we sit in our own homes comfortably. So I want everyone, all the students, to understand the perspective, the amount of work that has gone into bringing this. Plus, a lot of people are going through a lot of hardships, but despite that, they're continuing to do their work every day in trying to advance the field of quantum computing. It doesn't matter what's happening politically or government-wise in their countries. That's the most fantastic part about this whole collaboration that came together. It's almost like a worldwide collaboration while we're sitting here in Texas, in Dallas. It's like a worldwide collaboration came together just to get, the students that are here in this workshop access to these things. So there's been a lot of work that has gone in the background to do this. So I just wanted to bring that, and very grateful to everyone who helped to, initially when we brought the idea, everyone was like, it's not possible, right? You're talking about high schoolers that don't have a background in quantum mechanics, quantum physics. How are we even going to run a workshop of this order? Bringing these resources, it's tough because we don't have enough people. But in the end, the fact that it happened, I guess in that quantum world of superpositions, the probability of this, was 100%. So
it had to be.
It just happened, right? So having said that, I don't think there are any more questions. But Nithyasri, we would like to kind of get your view. If you want to take a look at your crystal ball, kind of talk a little bit about the current state of quantum computing that you see today, and where do you see it going in the next 10 years, that it gives them a perspective of if they are really interested in this field, and this is where most of the jobs are going to be in the future, what is it that they are really looking at?
Sure. I'd love to share that. But before that, I just want to say that I'm proud, and on behalf of Classiq, I'm very proud to have been part of this program, because it's very, very important to catch them young. They're the most enthusiastic at that time. And for me, my personal journey in quantum computing started out when I was in high school as well. So this is something that I personally am passionate about. I'm so happy that all of you could join today. And please, again, I would like to emphasize that you're very, very lucky to have been part of this program, learning from the best experts in the industry as well as the academia. So you should really be grateful to Rashmi, to University of Texas for this amazing opportunity. So let me, get started with some of the resources, because that is something that I had a difficulty when, I started out in quantum computing as a high schooler. So basically, the first place that generally people land up on is YouTube. And there's a lot of junk on YouTube when it comes to quantum computing. There's a lot of hype, that's surrounding this field. So it's very difficult to find out the right videos for you, especially as someone who's a beginner. There are more advanced videos that you might not be able to follow and not be able to find the correct resource. So I would give you, I think, a couple of things that you can start with. Firstly, I'm not sure if you guys still read books in your age, but I think it's a fantastic idea to do so. There's this book called Quantum Information and Computing by Mike and Ike. It is the Bible of quantum computing. I think it's a fantastic place to start. And secondly, if you know Python and linear algebra, you're already halfway there in learning quantum computing. So if you want to strengthen yourself in Python, of course, I'm sure there are a lot of resources available. But when you talk about linear algebra, I think I would like to suggest 3 Blue 1 Brown. It's a YouTube channel that they have really good videos. on the basic concepts of linear algebra, which will help you write down mathematically what superposition is, what entanglement is, and you're not just coding, but you understand the mathematics behind what's happening in your computer. So that's a fantastic place to start as well. And thirdly, of course, there are some blogs that every company has. Especially, I would like to iterate on our own blog at Classiq, where you can go and see tutorials. We have a very exhaustive documentation of the functions that we offer, of the inbuilt models of quantum algorithms that we offer. It's something that you can get started with for a more hands-on approach. And I would like to share one of my experiences. So I'm involved with the government of Singapore in their national quantum efforts. And what we do is we work more on the side of quantum simulation. So we're not running on real quantum hardware, but quantum simulation with the computational speedups from GPU side. So companies like NVIDIA, for example, who give us performance optimizations. So one thing that I would like to iterate, if you want to enter the field of quantum computing, you also have to think practically. Quantum simulation is the practicality behind quantum computing at this point. So when you see quantum computing, we have a very long way to go in terms of having a perfect hardware, which is no noise hardware. So there's this problem that I mentioned before, which is errors that occur in a quantum computer. And that is why there's a subfield in quantum computing called quantum error correction, if you're interested, which helps navigate these errors. So as of now, again, we still are a very, very young field. So quantum simulation acts as a prototyping for quantum computation. So if you're interested in getting into a practical level, you want to go into the industry, I think a fantastic place to start is to not ignore quantum simulation. Of course, it's always exciting to run on a quantum computer. But what happens is after a stage, you might be able to run with 20 qubits, 20 physical qubits. But after that, there are some problems that start to kick in. So what you can do is you go into quantum simulation and use some GPU resources, if available, to scale up your number of qubits. So that is one thing that I wanted to emphasize to all of you. And about the resources, especially, you would keep finding resources as you grow. As how much ever curious you are, you find as many resources that are suitable to you. One thing that I did personally was when I was, I think, in my 10th grade, I started reading papers in quantum computing. I'm not going to lie to all of you. I did not understand 90% of the papers, but I'm telling you, just a couple of years down the line, when I recall certain concepts that I read a couple of years ago when I didn't understand everything, it really rang a bell for me and helped me understand concepts. So I would say start reading papers, even if you don't understand them. Don't think that it's too advanced for you or anything. Just start reading papers, start reading books, especially the one that I suggested. Go into YouTube, find content that is appropriate to you. Well, maybe one fantastic place to get started would be Professor Elias Fernando's lecture series called Practical Introduction to Quantum Computing, which he gave at CERN. It'd be a fantastic resource for all of you. It's both a practical as well as a theoretical introduction. So I think these are some of the resources that you can go to build yourself in quantum computing. And I'm sure that you guys here are going to be the future quantum computing scientists.
Thank you so much, Nithyasri. I think I tried to catch every reference you were giving, but it would be really nice if you can add it to Slack. I think I found the three blue, one brown you mentioned.
That's right, for linear algebra.
Yeah, and that's actually very helpful because since you were looking at it in high school yourself and you were looking for all these resources, right. And I agree with you. There is a lot of information online which is not accurate. So we need to take things with a grain of salt, but to know the right channels to go to, I think that's really helpful. So your recommendation of this book, I think you mentioned Quantum Computation, Quantum Information, right? This is by
Michael and Isaac. Michael and Ike, as we call it.
Michael and Isaac. Okay. Yeah, I think I posted that on the chat. Sure. And then the last one you mentioned, Practical Introduction to Quantum Computing.
It is a lecture series that is available on YouTube. It is by a professor called Elias Fernandez. And that's a lecture series that I personally extremely enjoy.
As I'm in the midst of applying for residency.
Sorry. Yeah, I was just looking for it. Yeah. I think I found that. I'll post it but if you could post it to Slack just to make sure we got the right link.
I'll be happy to. Yeah, I'll be happy to share all of the resources that I mentioned. Yeah.
Okay. Yeah, that's a CERN lecture. I think that's what you mentioned from
That is right.
Introduction to Quantum
Yes.
Computing. Okay.
Yes.
Okay. Yeah, that's wonderful. Thank you so much. Actually, the conferences are probably one of the best ways to go. We just have a conference coming up in August at the Oak Ridge National Lab, and I'll share some more information in the classroom also. But open to you as well, Nithyasri. I think the deadline is July 17th for registration. If you want to take a look at it, it is here in Tennessee, and I think it's an in-person conference, August 12th to August 15th. But the who of all quantum computing world will be there speaking. It's a good opportunity. I guess they don't really have. I'm not sure what the criteria for getting in is, but at least go look at the webpage, take a look at what's available, what are the conferences going on.
Yes.
I think several conferences going on in Switzerland. They just had Quantum Basel, and I think a lot of different organizations are coming together. Again, it's kind of the starting time, but
it's a very global field.
Yes, very global field and very multidisciplinary. So I like your recommendation. Doesn't matter which field you are coming in from. You can come to quantum from electrical engineering, computer engineering, computer science, information science, what have you. You could come at it from physics, from mathematics. It doesn't limit what your background is. If you know linear algebra and you have an interest in physics, this is the place to be.
Absolutely.
Yeah.
Yes. And I would also like to add another point. One other thing that you're lucky to be having is that you are in the United States. It is a fantastic place for people who want to start out in quantum computing. One particular opportunity that I want to share with you, look out for what the national labs are doing. They have very interesting programs, mainly driven by NSF. They have an initiative called Q12, which is aimed at you guys, aimed at high schoolers to teach and disseminate knowledge on quantum computing. And why this is being done? It's because we don't have enough workforce for this field. There's a very young field, and people always think it's very challenging. So we don't have enough talented people to take this field forward, to be able to contribute to this field scientifically. So I hope that changes because of you guys.
Yeah. The other thing I also want to add is up until now, quantum was in the realm of the PhDs. And that's where we are trying to bring it down from the stars down to planet Earth. So do not feel intimidated. I know you were talking about reading research papers in 10th grade. I don't think that people should feel intimidated by the fact that there are all these PhDs and a lot of research going on. And that's where, we need to kind of bring that down to the masses, which is an attempt with this workshop, bringing high school students to it. Again, classical computing was very much in this phase, a few decades ago, but it did come down to the masses. Now we're going to have to do the same with the quantum computing. I guess this is the time we kind of grab it and try to pull it down. Yeah.
Absolutely.
Thank you so much, Nithyasri. This was really informative. Thank you so much. And thanks everyone for who joined and asked questions and worked with the problems. Really appreciate that. I guess we will end the call here. And thank you again. And we'll stay in touch on the Slack channel.
Absolutely. Feel free to reach out to me on either LinkedIn or my Classiq email ID, as well as the Slack channel. I'd be happy to help all of you.
All right. Great. Thank you. Thank you.
Thank you. Have a good day.
Good day. Bye-bye.